In the last video, we saw how we could visualize the different layers in our model and also get a summary of the layers in our model, which included the number of total parameters, the trainable parameters, and the non-trainable parameters. Now, let's have a look at how we might visualize our model's predictions so we can further evaluate how our model is performing. And so, to visualize predictions, if I could type correctly, it's a good idea to plot them against the ground truth labels. So in practice, you'll often see this in the form of something like y test or y true versus y preds or y pred, whatever you want to call it, where this is the ground truth versus your model's predictions. And so to do this, we'll first have to make some predictions. So we've got a trained model. So let's look at how we'll make some predictions to create y pred. Now, it's important here that y test is usually the nomenclature you'll see for the test labels. Same with y true. And y pred is also a very common nomenclature, so a variable name, for when you're making predictions with your model, or y preds, whichever you want to do. So model.predict, and we're going to predict on the test data set. So let's have a look. Y pred, see what our model comes up with. Okay, wonderful. We get a tensor in the same format as y test. There we go. So here are the ground truth labels, and here are our model's predictions. So in an ideal world, these would be the exact same numbers. So if our model learned the data perfectly and could predict the test data set 100%, these numbers would line up with these numbers. So rather than going through them one by one and comparing, let's see how we'll visualize them. So maybe we want to, how could we do this? How about we build a plotting function to figure this out? This is in case we wanted to, we're building a function because if we wanted to visualize our predictions going forward, we're probably going to reuse this plotting function. So let's create a plotting function. And this is actually, I'll put this down as a tidbit because I want you to remember something like this. I'll put a little key here. Oh, where'd my key emoji go? That's what we want. So note, this is just a Python concept in general too. If you feel like you're going to reuse some kind of functionality in the future, it's a good idea to turn it into a function. Nice and simple concept there. So if we did want to plot it, so let's go maybe def plot predictions, and then it's going to take some training data, which will by default equal xtrain. It'll also take some training labels, which will be ytrain by default. We also want some test data, which can be xtest by default. And then what do we want? Test labels. Yes, we need that. What comes after that? Oh, of course, we'll need the predictions. So the predictions can be y pred by default. Wonderful. And we'll give ourselves a little docstring here. So what can we call it? Plots, training data, test data, and compares predictions to ground truth labels. Nice and simple. We could talk about we could put in the docstring what the different variables are, but I'll leave that up to you. And so we want to start by creating a figure. We'll set the fig size to my favorite size, 10.7. Also a great hand in poker. Plot training data in blue. So that we're just basically taking the same plotting code as above. So this is where this is coming from. I'm not just pulling this out of the air. We're just functionizing this. You could just copy this and bring it down. But since we're in the habit of writing code rather than copying pasting code, let's get some practice. So we want a scatter plot here. And we're going to do train data and train labels. So we're just taking this, train data, train labels, and we're going to put the C into blue, and we'll give it a label of training data. Wonderful. And then we'll go plot testing data in green. PLT, we want a scatter plot. Again, the plots will differ here based on what kind of data you're working with. So scatter is pretty good for the problem that we're working on here, just a nice and simple regression. So label equals testing data. Beautiful. And here's where we're going to add the extra dimension or add the extra data set. We're going to plot models predictions in red. Nice and simple color scheme. Plot, scatter, and we want to compare them to the test data. So remember, we're passing our model to make the predictions. We passed it the X, so our predictions already have the X data built in, and they're predicting the Y value. So for our scatter plot for the predictions, it's going to, on the X-axis, plot the test data, which is X test, and then on the Y-axis, we want to plot the predictions. We'll give that a nice color of red, beautiful. And the label can be predictions. And of course, we want to show the legend just in case. We know the color scheme, but in case we wanted to share this plot with someone else, show them how beautiful our model is going, that should work. So plot predictions, train data, X-train. I mean, we could look at this all we want, but hopefully Python will tell us if we've got something wrong here. Now we're going to go plot predictions. We could almost just call this as it is, if all the variables are set up. Plot predictions. Boom. Oh, look at that. How good. That's some good predictions there. Now you see how this is, at least to me, I'm not sure, you can agree or disagree if you want, but to me that's something to really visualize how well our model is performing. So ideally, these red dots would line up perfectly with the green dots. But to me, that looks like something, hey, if I wanted to present this to someone else, they could pretty quickly pick up what's going on in terms of how good our model is. Now, of course, depending on the scale of this graph here, this distance here could actually be something that's way off. Now, that is where we'd want to actually compare these numbers in a different way. So I might just fill out this so we know what's going on. So train data equals X-train. We don't have to do this, but this is just for completeness. Train labels equals Y-train. Test data equals X-test. And then we go test labels equals Y-test. And then finally we finish the predictions with Y-pred. Wonderful. All right. So from the plot, we can see that our model's predictions aren't totally outlandish. However, as we said before, the distance here between these two, depending on the scale, could be a fairly large error. So the way we can figure this out is with some evaluation metrics. So let's cover that in the next video. So evaluating our model's predictions with regression evaluation metrics. So maybe before the next video, you can have a play around. Try and see if you can get that red line closer to the green line. And how you would do that is you would try to improve our model. So you go back up here, maybe add an extra layer, maybe change the optimizer, maybe fit it for longer, and see how close you can get the red line to the green line. Maybe you can get them to fully overlap. But otherwise, I'll see you in the next video. Welcome back. In the last video, we saw how we could evaluate our model's performance by visualizing the predictions. Now, that's one great way to do it, but the next best way, or you can actually say these are on par depending on what kind of problem you're working on, is to evaluate our model with evaluation metrics. Now, depending on the problem you're working on, there will be different evaluation metrics to evaluate your model's performance. And so, since we're working on a regression problem, two of the main metrics you'll see. Now, again, there are plenty. You can look these up. However, two of the main ones you're going to run into are MAE, which is mean absolute error. We've been using this one so far, which is basically saying, on average, how wrong is each of my model's predictions. And then you have MSE, which is mean square error, which is very similar to mean absolute error. However, you square the average errors, and find out. Yeah, so take the errors from your model's predictions, square them, and then find the average. So that being said, let's before we implement these with TensorFlow, let's have a look at the keynote. Here we have a slide for some common regression evaluation metrics. So let's start off with the mean absolute error, MAE. Here's the formula here, written in fancy mathematical notation. Now this is just saying these are our labels here, and xi, which could also be represented by y with a little hat. We'll see that in a second. Depends on where you find this formula. I think I just found this one on Wikipedia. What this is saying is these are our labels and these are our predictions. So across all of this, when you see this means sum of this little fancy looking E here. I think it's a Greek symbol for sigma. Now I want to give you a little tidbit here for math. So math kind of gets a bad rap, but it's actually a beautiful way of representing nature. So when you see these symbols, and I know when I first started in deep learning and machine learning, I saw Greek symbols like this and it would freak me out. But it's basically the same thing as learning code. So it wasn't until I started to replicate these formulas in writing actual code that I really started to understand them more. And so when you see this is sum of n starting from the first sample. So across all of our samples, so take the label, minus the prediction, get the absolute value of that, meaning that if the label is say 10 and this is 20, so this number would be negative 10, but we want the absolute value. So it's going to be, remember, if we did tf.abs, which is absolute, it would be positive 10. And then divide it by all of the predictions that you have. So all of the samples that you're making predictions of. And when you see this in combination, so this sigma notation here with n, in combination with the divide by n sign here, we'll see another form of it in a second. This is kind of like a fancy way of writing average. And this is the absolute error. And so we can do this in TensorFlow code. We're going to see this in a second. And when to use this metric? Well, this is a great starter metric for any regression problem. It's very easy to understand because it's just basically saying, I like to think of it as, on average, how wrong are our model's predictions? So then we go to the mean square error. So again, this is a very similar way, this little setup here, of writing the exact same thing as you see here. So when you see 1 on n in combination of sigma with an n on top, this is another fancy way of saying mean. And this here is another very similar way of writing, take our labels and minus the prediction. When you see a y like this with a little hat on top, this is often standing for, remember up in we created ypred. So this y with a hat means ypred or y predictions, and we square it. So see here we took the absolute value. In this one, we just square it with this little 2 here, and we can write TensorFlow code to do that. And when should you use this one? Well, this is a great metric to use when larger errors are more significant than smaller errors. Why? Because of this little square here. So if you've got a model and making an error of, say, an absolute error of 10 is okay, but an absolute error of 100 is just a catastrophe, you might want to use MSE because it's going to amplify the error value for larger errors or larger values because of this little square here. And then finally, we've got Huber, which has a little bit more complicated formula. We won't dig too far into that, but again, we can write this in TensorFlow code. But Huber basically takes the combination of MSE and MAE, and it's less sensitive to outliers than MSE, so mean squared error here. So with that being said, these are some common regression evaluation metrics. Take note of this slide. You'll see these in practice. There are many more. However, let's get hands-on and start writing them with code. We'll come down here. All right. So how might we start? So if we wanted to evaluate our model using evaluation metrics, one quick way that we can do that is evaluate the model on the test set. We've got our trained model here. We can go model.evaluate, x-test, y-test. Because if we pass the test data set here, remember we want to train on the training data set, evaluate on the test or validation data set. So we come here, check the docstring, returns the loss value and metrics values for the model in the test mode. So if we run this, what's it going to give us? Comes in the order of loss and then evaluation metric. So where did this MAE come from? So if we come back up here, when we created our model, remember when we compiled it? We set metrics equals MAE. We also set loss to be MAE. So for our model, in this case, because the loss and the metrics are the same, the evaluate method is going to return the same figure. So there we go. Now, that's one quick way to start evaluating it. How about if we wanted to run one of these evaluation metrics on their own by not calling the evaluate method? We just want to compare the prediction array that we have, ypred, to ytest. Let's see how we might do that. So if we come up here, we want another cell, and let's go calculate the mean square error. Actually, let's do absolute error first because that's what we have already. Now, before I do this, I want to issue you a quick challenge. I want you to see if you can figure out, we've got this slide here. We've got the TensorFlow code for how to calculate the mean absolute error. I want you to see if you can use one of these to calculate the same value as we've got here. So you're going to have to compare ypred to ytest. So probably try type out the code here and then read its docstring and see how you might use these values to calculate the mean absolute error. So give that a go, and I'll see you in the next video, and then we'll go through it together. How'd you go? Did you manage to calculate the mean absolute error? If you had a go and you figured it out, well done. If not, let's see how we might do it. So if we come back to the slide, we've got the code here, tf.metrics mean absolute error. Maybe we'll try this one because we've already seen this in our loss function. So let's see what this is. We'll start exploring the TensorFlow library. So tf.metrics.mean absolute error. There we go. Oh, here we go. Computes the mean absolute error between labels and predictions. Beautiful, that's what we want. So that's the function that it actually implements. So loss equals mean absolute ytrue minus ypred. Beautiful. Now how might we use this? Okay, loss equals tf.keras.losses.mean absolute error ytrue minus ypred. Now metrics.mean absolute error looks like it's the same as tf.keras.losses.mean absolute error. Well, I mean, it should be because it's the same formula, right? Now, ytrue, ypred. Do we have ytrue? We don't have ytrue, but we do have ytest. So let's type that in. Ytest and ypred. And actually, we might save this. So MAE equals that. And we'll set up the parameter names. Ytrue equals ytest and ypred equals ypred. See what happens. Oh, that's interesting. Now, MAE here gave us one overall metric, whereas this is showing us we've got a metric for each of our test labels and predictions. Why might that be? Well, we've actually got our predictions here and our test labels here. So what if we did ytest minus ypred? What happens there? Do we get the same output? Nope, we get a very strange output there. What if we did ypred minus ytest? We don't get the same output there. What's going on here? Let's have a look. Ypred, ytest. Now, is it because this is not a tensor maybe? Ypred? Let's turn this into a tensor and see what happens. So tf constant ypred, because if we do that, have a look here. This is what happens. tf.constant ypred. Okay, so now that's in a tensor format. Yep, that's what we want. And this is in a tensor format. Beautiful. This should work. We go here. Oh, same output as before. Let's have another look. What's the difference between these two? We'll go through it step by step. TF tensor shape equals 10, 1. D-type equals float 32. Now this is TF tensor shape equals 10, comma. That might be where I see. So they're not in the same shape. Now, this is a very important tidbit. So if we ever want to compare different tensors, remember how we did in a previous video, we had to reshape our tensors so that they could be in the same format or the right shape to do a dot product. Well, this is very similar when we're doing or running evaluation metrics. A lot of the time, TensorFlow is very smart, but it can't interpolate the fact that our ypred tensor actually has an extra dimension here compared to our ytest tensor. So, do you remember how we can remove the one dimension here of our ypred tensor? If not, that's perfectly fine. Let's revisit the squeeze method. So if we go tf.squeeze and then pass in ypred, what happens? There we go, much better. Gets rid of that one dimension there. So now our tensors ypred and ytest are of the same shape. So let's redo this. Calculate the mean absolute error. We could copy and paste that, but we're going to practice rewriting it. So calculate the mean absolute error. So let's see what happens if we go MAE equals TF metrics dot mean absolute error. Yes, that's what you want. Y true equals Y test. We're comparing, and again, this is another thing for all types of evaluation metrics. It usually involves comparing the Y true labels, so the true labels versus predictions. MAE. Oh, we forgot to TF squeeze our predictions. Shift and enter. Wonderful, look at that. How beautiful. So we get the same result as our evaluate function up here. Nice. Remember how I said a lot of the time you'll be spending your efforts reshaping tensors to make sure that they're in the right shape or the right format for whatever function you're trying to work with. Now we've done the mean absolute error. How about we try the mean squared error? So I'm going to leave this as a challenge for you. Calculate the mean square error. So just as we've done before, we've got the formula here, mean square error. Try out this function here and see if you can calculate the mean square error before the next video. How'd you go? Did you manage to calculate the mean square error? If not, let's see how we might do that. We'll go back to our little keynote here. And we can see here mean square error, MSE, is very similar to mean absolute error. So tf.metrics.mean square error. Let's go back here and go MSE equals tf.metrics.mean squared error. Y true equals the test labels. And ypred equals our predictions, our model's predictions, that is. MSE. Run. What's going on here? We should have one value. You know what we didn't do? We didn't remove the single dimension from our predictions. So let's do tf.squeeze. We're going to go here and let's see what happens. There we go. Okay. Now, MSE will be typically higher than MAE because if we come back to the formula here, it's because of this little square here. So the errors are typically larger, so the resulting singular metric will be larger generally than MAE. So if we come back, when should we use it? Well, MAE is a fairly intuitive metric. It says on average, how wrong are our predictions? However, when larger errors are more significant than smaller errors, so for example, if being 100 off is far worse than being only 10 off, you may want to pay more attention to the MSE. Now, you could try Huber, but I'm going to leave that to your own extension. For now, Since we're going to be running some modeling experiments in some upcoming videos, it's probably a good idea to, because we also functionized our way to visualize our predictions, let's functionize. I mean, this is pretty simple, but let's make a little function for mean absolute error and mean squared error so that we can use both of them going forward. So let's, right here, make some functions to reuse MAE and MSE. Def MAE, it's going to take in some Y true labels and Y pred labels. And then it's just going to return TF metrics dot mean absolute error. Y true will equal Y true, and Y pred will equal Y pred. Nice and simple. And then the same thing for MSE. Y true, Y pred equals return TF.metrics.mean squared error. Y true equals Y true, and Y pred equals Y pred. Beautiful. Now, do we need to do that? Not necessarily. However, it's good to have some helper functions ready to go for when we run some experiments. So let's do that in the next video. So for the past previous videos, we've made some predictions with a trained model. We've visualized them, so compared our model's predictions to the test data set. We've also evaluated our model's predictions with regression evaluation metrics, such as mean absolute error and mean squared error. Now, the next logical step you might be thinking is, how do we get these error values lower? So how do we minimize the difference between our model's predictions and the test labels? So in other words, get these red dots to be closer to the green dots. And so that's what we're going to tackle in the next couple of videos. More specifically, we're going to be running experiments to improve our model. Remember our workflow that we've discussed in a previous video? Usually start by building a model, fit it, evaluate it, tweak it, fit it, evaluate it, tweak it again, fit it again, and then evaluate it again, so on and so on. So if we come back to our keynote, if the Machine Learning Explorer's motto is visualize, 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 in other words, taking a look at our data, taking a look at our model, taking a look at our model's training, we haven't done that, but we will see that in a future video, taking a look at our model's predictions, and visualizing these wherever possible, well, the machine learning practitioner's motto, because we're an explorer and a practitioner, is experiment, experiment, experiment. And so that's what we're going to do. We're going to try run a series of experiments to see if we can improve our model following this workflow. We've already built a model. We've already fit it. We've already evaluated it. Now it's time to tweak it a little. We'll refit it. We'll evaluate it again, tweak it, fit it, evaluate it. So let's see what this might look like in practice. Or if we remember back, what are some ways that we can improve our model? The top three are probably, you'll see, get more data. So get more examples for your model to train on. In other words, more opportunities to learn patterns or relationships between features and labels. Number two would be make your model larger. We've seen this briefly before. So in other words, using a more complex model. That's what you'll often hear larger models referred to as, more complex. So this might come in the form of more layers or more hidden units in each layer. Remember how we added some extra layers to our models before? We also increased the number of hidden units in each of the layers. And number three is train for longer. So give your model more of a chance to find patterns in the data. So with these in mind, how about, since we've got our data set already, we've got X train, and Y train. This is our data set. How might we design? We can't really get more data unless we just artificially make our data sets bigger. So we'll rule this one out. But we can make our model larger, so use a more complex model, and we can train for longer. So let's design some experiments that we could do. How about we do 3 experiments? Let's do 3 modeling experiments. Now, what might you design? How about model number 1? What could we do for this one? So how about we do the same as the original model, 1 layer, but trained for 100 epochs. Number 2 could be model 2. This could be 2 layers trained for 100 epochs. And number 3, model 3 can be 3 layers, or maybe we won't change that. We'll keep it at 2 layers trained for 500 epochs. So 500 chances to look at the data. So see how we're just tweaking one parameter for each experiment. So the first one is 1 layer trained for 100 epochs. Then the second one, we're increasing the number of layers, but keeping the number of epochs the same. And for the third one, the difference is between the second model is the number of layers is the same. However, we're training it for longer. This is sort of the mindset I want you to start getting in. When you run your modeling experiments, start with, say, a baseline model, and then change one of the parameters for your next experiment, then do the same for the next experiment, and so on. You might want to, actually, I'll issue you a little challenge, is after you've seen us setting up these experiments, maybe you can create your own 4 and 5. So you can design them yourself. That would actually be some great practice. But let's get started. So the first one we want to do is, we'll create this. We're going to go build model 1. So what did we say? Same as the original model, 1 layer trained for 100 epochs. So we're going to set the random seed for as much reproducibility as we can get. Favorite number, 42, answer to the universe. So step 1 is create the model. So model 1 equals TF Keros. You could scroll up and see the first model that we built, or you could just take my word for it that it was just a singular layer here. TF Keros layers, not dense, not 1. There we go. And what's step number 2? When we're creating a model, we've created a model, what do we have to do? We have to compile it. So let's compile the model. Remember I said you're going to get a lot of practice writing this sort of code? Because that's what I want. I've said it before, and I'll say it again. I'd rather you learn concepts from writing code than from looking at slides. So the optimizer is going to be TF Keros optimizers dot. What did we build the first model with? Oh, look at that. We get a fair few options here. Now, there's actually a fair few optimizers built into TensorFlow. The main 2 ones that I regularly use is Atom and SGD. So we can go SGD. I'll let you research the other available optimizers that TensorFlow has. We'll set the metrics to MAE. Now if we go here, fit the model, model 1 dot fit. We're going to go X train, Y train. Now 100 epochs. That was the experiment design we were going to set up. So should this work? I think it should. Let's go. Shift and enter. Oh, look at us. Already modeling experts, sorry. So there's our first modeling experiment built. Now, what might we want to do if we're running experiments? What does a scientist do? Well, they track their results. So how might we do that? We've done it before. We created some functions before. What's the first one we might use? How about we visualize, or at least make some predictions with our model, and then we visualize them. Great idea. Make and plot predictions for model 1. So how do we make predictions with our trained model? We can we'll set up the prediction variable. we can call model 1, they'll predict. And we're going to make predictions, remember, on the test data. Because our model has never seen the test data, and we're interested in how our model performs on data it hasn't seen before. That's the real value of machine learning. Plot, we have a function, plot predictions. Oh, look at this. Look at us making our functions so we can just easily call them back again. Predictions, this is our docstring here, plots training data, test data, and compares predictions to ground truth labels. Now, we hard-coded some of these parameters, so the only one we have to change is the predictions variable, or predictions parameter. So predictions is going to be ypreds1, because we just created that. ypreds1. Let's see what it looks like. How'd our model 1 go? Oh, not too good. So we can see there's quite a large difference here between our testing data and predictions. Remember, ideally, these would line up here, but that's all in the nature of experimenting. We're going to try and improve it. So what else could we do? Well, we also created some functions to calculate evaluation metrics. Thank you, past us, for creating such easy-to-use functions. So create model 1 evaluation metrics. So we want MAE1 for model 1, by the way, equals MAE y test, and then we're going to pass it in ypreds 1. Beautiful. And then we're also going to do MSE1 equals MSE y test ypreds 1. And let's see what this looks like. MAE1, MSE1. Oh no, what did we do wrong here? We forgot to squeeze these variables. TF squeeze to get them into the same shape. Now, I guess what we could have done, if we knew that all of our prediction tensors had to be squeezed, remember, what does this do? If we visualize ypreds 1, if you ever forget what something does, just create a new code cell and run it. There we go, that's what it looks like on its own. And then if we squeeze it, ypreds 1, it removes that one dimension. So we have to actually turn this into a constant, a TensorFlow constant or a tensor to see that shape. So there we go. As the predictions come out, they have a 1 here, and it's our first axis dimension. But then if we squeeze it, it removes that 1 dimension, and it turns it into this tensor. So shape 10. So we can get rid of that now. And if we squeeze them, we can run that. Beautiful. So we see the error is quite substantially larger than what it was before. This is the MAE, so the mean absolute error. So on average, each dot is 18.74 away from where it should be. That's the mean absolute error. And if we square the errors, we see the error is even larger. Now, how about we change our MAE and MSE functions to automatically squeeze our predictions? So let's go up here. This is making our functions better. So TF squeeze. We'll go there. And TF squeeze. And we'll also go there. Shift and enter. Now if we come down here, we shouldn't need to run TF squeeze here anymore. Get rid of the extra bracket. Take note of the output here. Make sure it's the same. There we go. It is the same. Beautiful. Okay. Now that's model 1 done. So what was our second model? Model 2, 2 layers trained for 100 epochs. Now we didn't actually specify how many hidden units. I'm going to let you decide how many hidden units you should put into this second layer. So give that a try. We'll come down here. We'll go create a little note, build model 2, and then we'll just set up, so this is 2 layers trained for 100 epochs. Or we better say 2 dense layers. 2 dense layers, also known as fully connected layers. Now, our first model had 1 hidden unit in its 1 layer, but I'll let you decide if we're going to add a layer to model 2. So we'll set up model 2 equals something. I'll let you decide how many hidden units there are, and I'm going to make my decision on how many hidden units there are. So give this a try before the next video, building model 2. You could even calculate the model 2 evaluation metrics and plot the results if you're game enough. But otherwise, we'll go through our second modeling experiment in the next video. Alrighty, how'd you go? Did you set up model 2? Did you run the experiments? Did it go better than model 1? Hopefully these red dots were closer to the green dots. But if not, that's all right. Let's see how we can do it. So what's our first step? We might set the random seed, tf random dot set seed for as much reproducibility as we can get. So model 2, what did we say? 2 dense layers trained for 100 epochs. All right, so number 1, create the model, tf Keras sequential. And then we're going to come down here. So this one has 2 layers. We go tf Keras layers dense. Now, how many hidden units did you decide? If you built your own model, how many did you decide? I'm going to say 10 for this one. Remember, this is really an arbitrary number. We could set this to 1. We could set this to 10. We could set this to 100. I mean, most often you'll find values like this, like that are evened out. You'll rarely find values that are like 67, but you could try that if you want. So I'm going to try 10. tf Keras layers dense and 1. There we go. And I'm also going to, what do we do? After we've created the model, what's our next step? I've given you a little hint here. Compile the model. Now we have to do model2.compile. It's going to be the exact same thing. tf Keras.losses.mae. And then the optimizer is going to be tf Keras optimizers.sgd, just exactly the same before. And the metrics is going to be let's try MSE, you know, just to mix things up, because we're going to calculate our evaluation metrics anyway. So the only thing we've changed from our model up here is we've added an extra layer. Everything else is the same, except we're calculating the MSE as it's training. It's important to note that this metrics here will be calculated during training, and if you call, say, the evaluate method as we've done before on a trained model. So we come down, and what do we have to do once we've compiled our model? Step 3, fit the model. So model 2, we're going to fit on the same data, the training data, of course. X-train, Y-train, how many epochs are we going for? 100 epochs equals 100. You ready? Let's run our second modeling experiment. Boom. Oh. Wow, the MSE starts fairly high. Remember, MSE is often much higher than mean absolute error because of the squared value. So 1084, does it decrease by the end? Surely it does. Okay, finishes on 608. Let's see. Let's plot our, we've got to make some predictions. So make and plot predictions of model 2. So we'll call this one ypreds2 equals model2.predict on the test data, of course. And now we're going to plot our predictions using our beautiful plot predictions function. Woohoo! And again, all we have to change is this one. Remember, this is so helpful. If we're going to be running the same code over and over again, it's helpful to functionize it. We'll go Shift and Enter. What does this look like? Oh, yes. Very nice. So our red dots are a lot closer to the green dots. Beautiful. Come up here. Look at this one we did before. Looks like mud compared to what we've got here. So now we've plotted some predictions. Now let's calculate some evaluation metrics. So calculate model 2 evaluation metrics. You might want to pause the video and just go blaze right ahead and finish this video yourself. But if you don't want to do that, let's rock and roll here. MAE2 equals our function from before, ytest, and now ypreds2. We don't have to squeeze them this time because we've implemented that into our MAE function. And we can press Shift Command Enter. Oh, we should have actually put a doc string of what's going on here. But that's all right. We can do that later on for completeness. And then we want MSE2 equals MSE, Y test, compare it to our predictions with the second model, and MAE2, MSE2. Let's check them out. Boom, doesn't that look great? Oh, much better than before. 3.1 and 13. I think this is actually very similar to a model we've run before. But let's keep pushing on. We're now up to our third modeling experiment. So build model 3. Now, what was the experiment that we set up for model 3? We scroll back up. Lucky we took note of this. Here we go. Model 3. 2 layers trained for 500 epochs. Okay, so the only thing we're going to change between model 2 and model 3, we could actually just copy and paste this if we wanted to, and then change 100 epochs to 500, so we're fitting it for longer. However, as always, we're going to favor writing the code out again ourselves. So build model 3. It is 2 layers trained for 500 epochs. Now, you could sit here and watch me write this out, or you could just skip ahead and write out the model 3 code yourself, plot the predictions, and evaluate it using evaluation metrics, and I could just see you in the next video. Otherwise, if you want to stay on board and we want to write this together, let's do it. So let's set the random seed. So tf random set seed. And then we go, what's step 1? Create a model. Oh, we are getting some prime experience here. tf_kerers.sequential. Open up our list. We come back. What did we say? 2 layers. We're going to keep it exactly the same as model 2. So I believe it was a dense layer with 10 hidden units. Wonderful. And then another dense layer with 1 hidden unit, because that's going to be the output layer. And then we're going to, what do we have to do? After we've created a model, what's our step? Compile the model. I mean, by the end of this, you're going to be like, Daniel, you are a broken record. But that's all right. If you're writing TensorFlow code like it's nothing, well, then I've done my job. Kerers losses.mae, and we're going to go optimizer equals tf kerers optimizers sgd. Wonderful. I'm going to set up our metrics. This time we'll revert back to MAE just to spice things up. Oh, too late. Oh, well, optimizers. Oh no, we've made a typo there. Classic. And now we're going to fit the model. So model 3 dot fit x train y train. How many epochs are we doing it for? What's our third experiment? 500. Oh, nearly did 5,000. Far out. That would have been interesting. I mean, you could do that. That's a challenge for model 4 maybe. 5,000 epochs. We'll see how this one performs first. Shift and enter. There we go. It's going to take a little bit longer, but not too much longer because it's only a small data set. But look at that. We can get ready to make and plot some predictions. Oh, what did it? Before we do that, MAE, I would have expected that to be lower maybe if we were training for longer. But again, don't just trust the training metrics. Let's visualize our model's predictions and run our evaluation functions. So let's go ypreds3 equals model3.predict. And we're going to do it on the test data set. Beautiful. And then our wonderful plot predictions function. We're going to set the predictions variable to be the predictions for our third modeling experiment. This should be preds3. Let's have a look. Oh, golly gosh. That's even worse than the first model. That's terrible. Far out. What's happened here? You know what? I think our model is trained for too long. We've totally missed the Goldilocks zone of where we should train it for. So this is a prime example of how tweaking some hyperparameters of your model, even ones that you intuitively think should result in a better result, actually don't lead to a better result. And we've actually just experienced here probably the first time we've come across our model overfitting, which is a very important concept in machine learning, but we're not going to cover it now. I'll leave that for a future video. However, if you want to look it up, I would search overfitting. Essentially, it means that the model has learned the training data too well, and it doesn't generalize very well at all to data it hasn't seen before. So give that a look in your spare time as a little extension to this video. But let's run our evaluation metrics for completeness. So calculate Model 3 evaluation metrics. We'll do our MAE3. For Model 3 is MAE. We'll compare the Y test labels to the Y preds for the third model. Wonderful. And then we'll do the MSE3 equals MSE Y test Y preds 3. And then we'll have a look at MAE3, and we'll also have a look at MSE3. Whoa. Now this is substantially higher than our other models that we ran. I think Model 2 was actually the best one. Now, what we might do is rather than just scroll back and forth comparing our model's metrics, like we could look at that one, yep, Model 2 is the best. Let's put them into a more structured manner. And so in the next video, let's look at how we might comparing the results of our experiments. So we've run a few experiments now. Let's compare the results. So in our workflow, we've said before, come back to the keynote, the machine learning practitioner's motto is experiment, experiment, experiment. But as you might have guessed, any budding practitioner or any budding scientist doesn't just experiment relentlessly. They do a few, compare them, see which one works, and then they disregard the ones that don't work and move forward with the ones that do. So let's see in the next video how we might compare the results of our experiments. Welcome back. So we've run a few experiments. Now it's time to compare the results of our experiments to see what worked and what didn't. Now again, we said we could just scroll back up and check the numbers, but that's not really a structured way. Like we've only done 3 experiments, and already it's getting tedious to just go back through and see what works and what didn't. So the beautiful thing is that we've saved all of our model results to different variables. So to compare them, oh, actually, wait, I just want to put a little tidbit here. Something that I just thought of as I finished the last lecture is note. You want to start with small experiments and make sure they work. So by small experiments, I mean small models. And then increase their scale when necessary. Because what's our motto as a machine learning practitioner? Experiment, experiment, experiment. And it's hard to run a lot of experiments when you're trying really large experiments all the time. So start small, like we've done up here with our first model, Model 1. We started with 1 layer. And then we started to increase the complexity as our experiments went on. So just keep that in mind when you're running experiments. Start small, build up, add complexity when needed. So let's go down here. And if that doesn't make sense for now, we're going to see that a lot throughout the course. It's going to be our theme, is start small, build up when needed. Let's see how we can compare our results. So how might we do so? Well, how about we create a pandas data frame, which is just a table so we can compare our results of a different model. Let's compare our model's results using a pandas data frame. So the beautiful thing about Colab is that it's got pandas inbuilt. Import pandas as PD. And then we'll probably set up our model results as a list of lists. So we can pass it to our... So model 1 can be MAE1, MSE1, and then model 2 can be MAE2, MSE2, and then model 3 can be MAE3, MSE3. Beautiful. And then to create the data frame, how about we call it all results? And then we'll go PD data frame. And then the first thing we'll pass it to is our list of lists, so model results. And then we can set up the column names. What should we call the columns? Well, we have models, MAE, MSE. That's nice and easy. So model, MAE, MSE. Beautiful. And now what does this look like? Is this going to work? It worked, but that's a little hard to read. You know what we can do here? We can just get the numpy value of all of these. So we go .numpy. Maybe we could have built this into our functions up above, but because we're already here, we'll just do some hacky code to get it looking nice. But when you're writing your code, you're going to make it beautifully functionized, aren't you? Let's see this. There we go. That looks much better. So, from our experiments and comparing our results in this beautiful table, I mean, maybe if you run a few more models down here, you may have model 4, model 5, model 6, etc., etc. It looks like model 2 performed the best. So what was our model 2? Model 2.summary. So it looks like it had 2 layers. So one with 10 hidden neurons and the output layer with 1 hidden neuron. And it was fit for, we can come back up here. We can see it up here, model 2, 100 epochs. All right. So, what can we do with this? You might be thinking, comparing models is very tedious. And it definitely can be because we've only compared 3 models here. But this is part of what machine learning modeling is all about. Trying many different combinations of models and seeing which performs best and actually seeing which doesn't perform best. So each model we ran is an experiment to figure out what doesn't work. And I'm going to put a tidbit here, is that we'll just write here, looks like model 2 performed the best. Wonderful. So the tidbit, the takeaway here is this is a follow-on from before. So we said start with a small model, and another one is one of your main goals should be to minimize the time between your experiments. So that's why we start small and build up when needed, because as we said before, if you're having to wait like 10 minutes between each model experiment, and sometimes you will have to with a larger data set, as we'll see in future videos. But the more experiments you do, the more things you'll figure out. Now this is getting too big because it's not a markdown cell. The more things you'll figure out which don't work. And in turn, when you know what doesn't work, you will get closer to figuring out what does work. It takes a lot of trial and error. Remember, the machine learning practitioner's motto: experiment, experiment, experiment. By the end of this course, you're going to have that tattooed on your brain, as well as, if in doubt, run the code, and as well as visualize, visualize, visualize. And so another thing here is that what you think might work, such as with Model 3, we increase the number of epochs, so the number of times Model 3 could look at the data. Sometimes intuitively you'll think it will work. We mentioned this in the previous video, but it in fact turns out to be the exact opposite. So look what happened with Model 3. So that's why experiment, experiment, experiment is so valuable. Now you're probably wondering, it's like, Daniel, hey, we saved all of our results here and we kind of set up a pandas data frame and we had to save all of our evaluation metrics to different variables. I mean, you say here, we're probably going to run potentially dozens of modeling experiments per problem that we're working on. That's going to end up very tedious and a lot of different stuff all over the place. And you're exactly right. Well, the good thing is that the people, like machine learning practitioners around the world, have developed solutions. And so I'm going to put here, tracking your experiments. These are a couple of little extensions for now, but we are going to cover one of them in the future. So let's just put here, one really good habit in machine learning modeling, as you may have seen, is to track the results of your experiments. And when doing so, it can be tedious if you're running lots of experiments. Luckily, there are tools to help us. So the first one, this is a resource. We're going to put the little resource emoji here. resource. Remember, all of the resources, exercises, extensions, etc. in the course GitHub, as well as going to be links there'll be links where you can find all of these things. So resource, as you build more models, you'll want to look into using. So one of my favorite tools built straight in TensorFlow is TensorBoard. So this is a component of the TensorFlow library. And again, I'm just introducing the names of these things now, but later on we're going to get hands-on. So this is TensorBoard is a component of the TensorBoard library to help track modeling experiments, a very important part of machine learning, and we'll see this one later. And another one of my favorite ones that links straight into TensorBoard. There's a fair few of these on the market, but this is the one I have the most experience with. It's called weights and biases. So a tool for tracking all kinds of machine learning experiments. And the beautiful thing is, plugs straight into TensorBoard. So if you're using TensorBoard, you can definitely use weights and biases. So if we have a look, we can search up TensorBoard, tensorflow.org/TensorBoard. Here we go, TensorFlow's visualization toolkit. We're not going to dive too deep into this. If you want to jump ahead and have a look at what TensorBoard is capable of and maybe even plug it into our models, you can check it out. Otherwise, the other one is weights and biases. One of my favorite external tools for machine learning. But since this is outside TensorFlow, we're not going to be covering weights and biases. You can look into that as some extra curriculum if you want. We will be seeing TensorBoard later on. But for now, that's all we're going to cover for tracking our experiments. In the next video, if we've trained a model, say model 2, and we wanted to use it, say, in one of our applications, what we might want to do is get it out of our Colab notebook and somewhere else. So let's look in the next video at saving our models. So we've trained a few models, and we found out that from our modeling experiments, model 2 is performing the best so far. So let's say we wanted to save that model. Like right now, it's just sitting in our Jupyter Colab notebook. It exists as a Python object here. How would we save that and export it somewhere else? So let's figure out how we might do that. I'll just put a note here. Saving our models allows us to use them outside of Google Colab or wherever they were trained, such as in a web application or a mobile app. So how might we save a model in TensorFlow? This is where I'd start if I wasn't sure. I'd look it up. There we go. Save and load models. All right. Caution, TensorFlow models are code and it is important to be careful with untrusted code. See, using TensorFlow securely for details. I'll let you have a look at that, but trust me, we're not using TensorFlow maliciously here. Now, we've got a few options here. So defining a model. They've created a function here to define a model, model.summary. Here we go. We could save checkpoints during training if we were training for a long time. We're probably actually going to have a look at that later on in the course. But where is the save model function? What if we go save? There we go. Model.save. Save the entire model as a saved model. Now, in TensorFlow, there are two formats, or two major formats of which you can save a model to. The first one is the saved model format. So the saved model format is another way to serialize models. Models saved in this format can be restored using tf-keras models.load model. Okay. So that's, I'm guessing, once we've saved our model. If it's in saved model format, we can load it in using this method here. And are compatible with TensorFlow serving. We haven't seen that, but if you wanted to look it up, that's something you could look that up. The saved model guide goes into detail about how to serve/inspect the saved model. All right. Well, we've read up a little bit about it. Let's try it. Oh, and what's down here? Another format. Okay, so it looks like there's two formats that we can save our models in, but they're both using the save method. And one has a .h5 extension, HDF5 standard. All right, well, let's try one at a time. So how might we save a model? Or we'll put a note here. There are two main formats we can save our models to. Number one, the saved model format, and number two, the HDF5 format. Now, I believe the saved model format is the default. Actually, I know it is because I have experience with this, but let's just see. So save a model using the saved model format. Now, we can do so, go model2.save. And then if we check out the doc string here, saves the model to TensorFlow saved model or single HDF5 format. Okay. The save file includes the model architecture, allowing to reinstantiate the model weights, in other words, the patterns our models learned, the state of the optimizer, allowing you to resume training exactly where you left off. That's handy. All right, so let's try it out. So what was the parameter we have to pass in first? File path. Or let's call it something simple. You might want to get more creative with your model naming. So I'm just going to call mine best model saved model format and shift and enter. What happens here? We get a whole bunch of warnings. So I've looked at these warnings before, and they come up a lot of the time when you're saving a model. Essentially, what it is some behind the scenes libraries that have been updated. And if you're just using the save format, you can safely ignore these. You can also find what the warnings actually are in this documentation here. But just for now, trust me, the save model format, if these warnings come up, it's all right. Unless you're getting some sort of failed, the model hasn't saved correctly. But in our case, let's have a look at what happens. We check the Files tab of Google Colab, and here we go. We get best model.
Hello, I'm not going to interrupt for very long, but just want to give you a congratulatory message on making it 7 hours, 7 minutes and 7 seconds into this video. Oh, my screens have gone blank. But just wanted to remind you, if you're enjoying what you're watching and coding along with, if you want to sign up to the full version of the course because you've made it this far, I have a little present for you. If you go to the zerotomastery.io website and decide to sign up to the TensorFlow Deep Learning course and use the code TFLW, TFLW, you'll get 15% off your sign-up price. But keep this a secret, will you? Because I want to keep this as a surprise for people who've made it this far through the video. Anyway, that's all I wanted to say. Use the code TFLW for 15% off. And don't tell anyone else. You can tell your friends, but please don't leave this in a comment in the video because people like surprises. Anyway, I'll see you later.
Saved model format. And in this file, we get a few things. We get assets. Okay. So we got what's in here and what's in the variables. And we get saved model.pb. Now this .pb format is called a protobuf file. Again, you can find more on this in the save and load documentation. But to make sure that our model's saved correctly, one of the best ways that we can do it is by loading it back in and checking it out. But before we do that, how about we save a model in the HDF5 format as well to test that out. So let's search that. HDF5 provides a basic save format using the HDF5 standard. All right, what's the HDF5 standard? Hierarchical data format. All right, is a set of file formats, HDF4, HDF5, designed to store and organize large amounts of data. Okay, well, I'll let you know that going forward, you're probably going to start training some fairly large models. And sometimes you might need to store them in a universal data format. So something like HDF5. So something that you can pass around to many other different programming applications. And TensorFlow allows us to save our models directly to .h5 by adding the h5 extension onto the end of our file path. So let's have a look at that. We're just going to run the exact same code up here, except one difference. Save model using the HDF5 format. Now, which one of these should you use? Well, it's really going to depend on your use case. If you're staying within the TensorFlow environment, so you want to just use your model with pure TensorFlow code, you're probably better off using the saved model format. However, if you're going to use your model outside of pure TensorFlow code, maybe HDF5 is better off for you. But we're getting a little bit ahead of ourselves here. Just know that there are two main formats that you can save your saved models to. The save model one is also the default, so the majority of use cases you'll probably be using the saved model format. Now let's see what happens if we run this. See how we've just got the exact same code here, but all we've done is we've changed it to have .h5 on the end. We'll run that. Beautiful. Now what happens? There we go. So you'll notice the main difference here as well is saving a model to the saved model format. We get a folder here. And to the .h5 format, we get a single file. Now, I mentioned before that a way that we can check to see if our models have saved correctly is by loading them in and testing them out again. So much like we've evaluated our model 2, I'll just close this to get these evaluation metrics here. If we load our model back in, if the documentation is correct, saying that it's saved all of its weights and optimizes state, when we load our model 2 back in from its saved model format or the H5 format, theoretically it should get the same results as before we saved it. So in the next video, let's see how we can both load a model in and reevaluate it to make sure it's saved correctly. Welcome back. In the last video, we saw how we could save our models or a trained model. And we saved them both to, or model 2, which is the best performing model so far, to both the saved model format and the HDF5 format. So we've still got our models here in the Files tab of Google Colab. Now, what if we wanted to load that model back in? Let's see how we do that. Loading in a saved model. So if we come back to the documentation where we looked at load and save models, there we go. So new model equals tf-keras models.loadModel. Now I believe if we go load model, there we go. Models saved in this format can be restored using the tf-keras models.loadModel method. Now the beautiful thing is that with both formats in TensorFlow, the save model format and the HDF5 format, we can use the same method to load them in. So let's see how we do that. Which one do we want to do first? Load in the saved model format model. And let's do, what could we go on? Loaded saved model format equals tf.keras.models.loadModel. And then we're going to pass it the file path of this folder here. Now in Colab, you can do this by copying the path. So I'll just show you that there. We can copy the path there, turn that into a string. Now, again, in Colab, you're going to get a little content in the front of it. I believe it works regardless of whether you have content in the front or there or not. So we could do it like that. Hopefully that works. Otherwise, we can just revert back to what we want. Load save model format. How should we evaluate it? Oh, we'll get a summary. That's how we do it. Summary. Let's see if this works. Beautiful. Now, is this the same as our model 2 above? We've got 2 layers, dense, with 10 hidden units, and another one here with 1 hidden unit. If we go model 2 dot summary, is that the same thing? Yes, beautiful. Now, to see if our loaded saved model format model, far out, we're going to say model a lot here, aren't we, is actually still the same as model 2, because right now the architectures we've confirmed are the same. And these are the same here. However, in the documentation, it told us that it's going to save the weights as well. So in other words, the patterns model 2 has learned. So to really check that, how about we make some predictions with model 2 and the saved model loaded model, and then compare those predictions to make sure they're making the same predictions. Because if they are, that means the patterns they've learned should still be the same. So compare model 2 predictions with saved model format model predictions. So this is kind of like we're writing a test to see if our models are the same thing. Our loaded model and our saved model. And we're going to go loaded saved model format preds equals loaded saved model format dot predict on X test. And then to compare them, we could do, let's just test them for equality. How about we do that? Loaded saved model format. This should return true. False, 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 false. What's happened here? Let's have a look at model 2 preds. And loaded saved model format preds. Five, 2, 8, 1, 3, 9, 9, 1. They seem pretty comparable to me. What we might have to do is, how about we calculate the mean absolute error of each? Otherwise, we might have to bring in a numpy function here. So MAE, we want MAE of y true equals y test, and y pred equals, this is going to be model 2 preds. And then we want to compare these two to MAE y true equals y test, and y pred equals loaded saved model format preds. So they should have around about the same error. How does this go? True. Beautiful. So I'm not sure why their predictions are different. You know why it might be? It's because of how a computer stores numbers. So if we go model 2 preds, have a look at this. Maybe we'll squeeze that so it's, by the way, you can do dot squeeze on the end if you wanted to. That's a numpy method coming in there, I believe. Yeah, there we go. And then if we do loaded save model preds dot squeeze, I believe these two should be very similar. Yeah. So why aren't that? If we copy this up here, we're going against our rule of always writing code. Should this equal true? True, 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 true. Okay. So I would say the reason why here we're not getting this correct is because dimensionality-wise, they aren't of the same shape. Is that why? But that doesn't make sense. So this is I want you to experience this. This is me exploring an output that I didn't really expect while I was creating this video. So I really want these videos to be as if like we were sitting side by side and coding and figuring things out together. That doesn't work. Okay. Oh, you know why? Because it's not preds. Haha. What a simple typo. Did you catch that? Why didn't you tell me earlier? Haha. This is a challenge we face when we're bringing in so many similar variable names. Now this should work. Okay, true, 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 true. All right, all that extra code there we wrote, well, the news is we didn't have to write it. So, I mean, you're going to see these things happen a lot of the time. And I'm glad you're watching me make mistakes on the fly because, as you learn, you're probably going to make a lot of mistakes too. Now, we've loaded in a model using the save model format. How about we try the H5 format? So load in a model using the .h5 format, and we're going to go loaded h5 model can be tf keras models.load model, and then we're going to pass it in just the file path. We can come over here, copy the path if we wanted to, Command V or Control V depending on if you're on Windows. Going to turn that into a string, get rid of that. Now again, you don't necessarily need content, but just to check if it works. So that's the loaded model, and we'll get the loaded h5 model.summary just to make sure it's the same thing. Does this match our model 2 summary? I believe it does. Model2.summary. So first things first, that's nice and easy to check. The architectures are the same. Now we're going to check it to make sure its predictions are the same as model 2. So if we go here, check to see if loaded .h5 model predictions match model 2. So we can go model 2 preds. We've already got that variable, but we'll just have some practice writing predict on x tests, writing some more code. It never hurts to write a little bit more code. And then we'll go loaded h5 model preds equals loaded h5 model dot predict on x test. And then if we want to compare them, we can remind ourselves to this time add preds on the end, Daniel, equal loaded h5 model preds. How do we look here? True. Beautiful. We could do the same again for working out the MAE, but I'm just going to, if all the predictions are the same, the MAE should be the same as well. So we can get rid of this extra one and maybe move this one up to the loaded save model format. We'll just put a note in here of what we did so we don't confuse ourselves when we come back to our notebook. Compare the MAE of model 2 preds and loaded saved model preds. So what we just did, we repeated ourselves writing the code here. If you wanted to sort of functionize this going forward, that could be one of the tests that you run. So say, for example, you saved a model and then you loaded it back in. You could write a little function to make sure that the loaded model has the same prediction values or error rate or summary or something like that as your saved model. That way you make sure you're using the same the model with the same learned patterns. But otherwise, in the next video, we have our files here in Colab. How might we download them to our local machine if we wanted to use them outside of Colab? Let's check that out. Welcome back. So we've seen how we can both save a trained model and load it in within a Google Colab notebook. And by the way, a lot of these methods will work in just a Jupyter notebook. But how might we download a model or any other file from Google Colab? Now, this will be this lecture specifically if you're using Google Colab. If you're using a Jupyter notebook, oftentimes your files will be on your local machine or on your server hosted somewhere else. But this is specifically if you wanted to get a file off Google Colab. Now, we've got a couple of ways. So the first one, number one, or if you want to download your files from Google Colab, number one is you can go to the Files tab and right-click on the file you're after and click Download. So let's try that out. So Files tab, this is this one here. We have code snippets, we have search, we have table of contents. Far out, look how much we've covered so far. You should be really proud of yourself. But we'll come into the Files tab because that's what we're trying to do. And say we wanted to download our best model HDF5 format, .h5, we could just go here and click Download. Now, depending on the size of the file, will depend how long this takes. But now if we check My Files, Downloads, I've got the best model HDF5 format saved here in my download. So if I wanted to import that into some sort of application or into another coding environment, I've got it saved and trained here. Now, the second option to download a file from Google Colab is we can use code. See the cell below. Let's write some code to download from Google Colab. If we want to download a file from Google Colab, we can import from google.colab, import files, and then files allows us to files.download, and then if we just pass, we'll copy this one, see if we can download it again, copy path. We pass in the file path of our .h5 model, shift and enter. Oh, has no attribute downloaded. Oh, type that in wrong, so don't type in downloaded like I did, just type in download. And here we go. We're going to get a little loading bar, and there we go. We've got another copy of it. So we'll check the downloads. Oh, there we go. We've got the same file because I've got a little 1 here because we downloaded it twice. But that is a quick and easy way if you wanted to download your files from Google Colab. Remember, depending on the size of the file and your internet connection, it may take a little while to download. So just be patient. The other way is, maybe a third way is if you wanted to, while we're here, you can save it to Google Drive by connecting Google Drive and copying it there. So see second code cell below. So let's see how we might do that. I'm going to mount my Google Drive. So this is going to, if you have a Google account, which you kind of require to sign into Google Colab, it's going to mount your Google Drive, which is online cloud storage hosted by Google. We're going to wait for this to load. And when it loads, we should see our Drive file appear in the Files tab. Beautiful. So this is my Google Drive here. If I open that up, I've got my Drive, and I've got a few other things that I'm working on there. Wonderful. So if I wanted to save it here, copy path, or actually copy path there. Let's save a file from Google Colab to Google Drive. This requires mounting Google Drive. So we can do bang CP for copy. So we're going to copy this file here, H5. So that stands for copy this file at this path to, which path do we want to go to? I believe I might have a TensorFlow course. I'm going to copy that path. Now you might have to create a file in your Google Drive called TensorFlow course. You might be able to go new folder and create something like that. But mine's called TensorFlow course. It's already existed. So there we go. Copy best model HDF5 format.h5 to content drive my drive TensorFlow course. Let's see if this works out. All right, that looks like it went through pretty quickly because it was a relatively small file. So let's go ls and then just the path here to see if it's copied across. Oh, best model HDF5 format.h5 and a little spoiler alert for what's to come, but I'm not going to talk about that for now. We're going to see that in upcoming videos. So there's 3 ways there. If you wanted to download a model or any other file from Google Colab, you can right-click and click download. You can download it with code. Or if you wanted to save it to your Google Drive and access it later, you can use the copy method to save it across there in your target folder. Alrighty, so we've been through a fair few of the fundamentals. In the next video, or in the next series of videos actually, let's have a look at how we might tackle a larger example. And I'm not going to say any more. I'm going to wait until you're in the next video to show you what's going to happen. I'll see you there. I've said it before, and I'll say it again. We've covered a lot of ground so far. I mean, we've seen the fundamentals of building neural network regression models in TensorFlow, so you should be proud of yourself. Look at all the subheadings we've covered. Give yourself a pat on the back. But now it's time to step it up a notch and build a model for a more feature-rich data set. So have a look at our data. Look at what we've been playing with. X-train and Y-train. Just a couple of tensors with single numbers trying to predict single numbers. But in practice, you're probably going to be dealing with a little bit more of a complex data set. So what data set are we looking at? Well, we're going to have a look at the publicly available medical cost data set, available from Kaggle and hosted on GitHub. So let's find it. So medical cost data set. Here we go, medical cost personal data sets from Kaggle. Now, Kaggle is a website which is basically an incredibly great place to compete in data science competitions, find different data sets, see example notebooks, and also learn more about data science and machine learning in general. So you're going to become very familiar with Kaggle over your data science and machine learning explorations. So we're not going to go through it for now, but just know that if you want example data sets, Kaggle is probably one of the best places to find them. Now, if we have a look at this, so medical cost personal data sets, Insurance forecast by using linear regression. Let's have a read of what's going on. So context, so machine learning with R. So R is another programming language that can be used for numerical computing, just like Python, by Brett Lantz, is a book that provides an introduction to machine learning using R. Okay, so the long story short here is that this is a data set that's available online, and we've got a bunch of columns here: age, sex, BMI, children, smoker, region, charges. Now what we're trying to do here is use these columns, so age through to region, to predict what someone's individual medical costs billed by health insurance will be. So we're using these features here to predict a number. So it's a regression problem. I believe this example has used linear regression, but we're going to build a neural network regression model. So the dataset is publicly available on GitHub here. Wonderful. So there's a fair few data sets here. We're looking specifically at insurance.csv. Now I'll show you a little trick that we can use to import this straight from GitHub to our Google Colab notebook. If we go raw, there we go, raw.github user content. Now, if you can't find this link, I'll put in the resources section for you. We're going to copy this link, come back to our notebook. I'm going to get out of this. And the first thing we're going to do is actually import the required libraries for this larger example. We've already imported these, but it's good practice just to, if we were starting from scratch, import TensorFlow as TF, import pandas as PD. Wonderful. And we're going to also need matplotlib in case we want to do some plotting. Those libraries are pretty standard. So now, because we've got the insurance data set copied to our clipboard, read in the insurance data set. Let's see what it looks like. We'll call it insurance equals pd.readcsv. And then the beautiful thing is we can just paste a link in here, and the read CSV function will read it directly from here. All of these values. So there's the columns: age, sex, BMI, children, smoker, region, charges. We can import directly. Let's have a look. Insurance. All right, so 1,338 rows times 7 columns. Yes, now we're talking. This is a little bit more complex than the problem we've been working on so far. So what do we have here? We have age, sex, BMI, children, smoker, region, and then charges. This is an amount. So this is how much someone's medical costs or medical bills were, medical insurance was based on their age, sex, BMI, number of children, are they a smoker, yes or no, and whereabouts do they live? Southwest, northwest, etc. I'm not sure. Is it from a city? Anyway, doesn't matter. You can do some research. I'll put the links to where you can find this data set. Essentially what we're focused on here is writing TensorFlow code to take in these features, learn the relationships between them, or more so the relationships between these features and this target variable here, charges. So what is a regression problem? Relating it back to our Wikipedia definition, in statistical modeling, regression analysis is a set of statistical processes for estimating the relationships between a dependent variable, often called the outcome variable, and one or more independent variables, often called predictors, covariates, or features. So in our case, what is our dependent variable? Our dependent variable is the charges, because this is what we're trying to predict. And what are our independent variables? In other words, known as, I like the term features. So that's what you'll hear me use a lot. Our independent variables are these columns here: age, sex, BMI, children, smoker, region. So what do we have to do? What is our first step in getting our data ready to pass into our machine or neural network models? Can we just start building a model? Model equals TF Keras sequential. I mean, we could keep that going, but what do our machine learning models like? Can we pass in this column, sex? If it reads female or male, what's it going to do? So if I go insurance, what type is this column? Oh no, insurance. Data type object. Well, what about smoker? data type object. What's the difference between smoker and insurance age? Int 64. So we have some columns here that are numerical and some columns that aren't numerical. Do you remember what we have to do to non-numerical columns before we can pass them to a deep neural network or a machine learning model? We have to turn them into numbers, right? If we come back to our regression inputs and outputs, say we're trying to predict the price of homes, the sale price of homes, based on the features here, bedrooms, bathrooms, garages, before we can pass it to our machine learning algorithms, we have to create a numerical encoding, which is often referred to as input features. So that's what we're going to have to do to these variables here. Now, one style, we've covered one style of numerical encoding, and it's the style we're going to use for this problem. It's called one-hot encoding. So if we go, what is one-hot encoding? Probably one of the simplest methods to turn categorical variables into numerical variables. So if we go here, is there a diagram? Maybe we just go to images. There we go. Nice and simple. So one-hot encoding, if we have the food name apple, chicken, broccoli, for one-hot encoding, apple gets a 1 and 0 for everything else. For chicken, chicken gets a 1 and 0 for broccoli and apple. For broccoli, broccoli gets a 1 and a 0 for chicken and apple. So that's what we want to do. Because we're working with categorical variables here, we're going to create a column that is maybe sex underscore female. And if the value of this sample is female, we want to put a 1 there. And if it's male, we want to put a 0 for the sex underscore female column. Now, we could do this manually, but that's going to take a whole bunch of work. So what I prefer to do is use, if we go to pandas data frame, we can use pandas get dummies function. Let's see what this is. Or better yet, if you didn't know what this function was called, how to one-hot encode a pandas data frame. What do we get? How can I one-hot encode in Python? One-hot encoding a feature on a pandas data frame. Examples. What do we get from this web page? Again, I'm not sure what this web page is going to show us, so this is kind of running the gauntlet here. All right, there we go. With one-hot encoding, a categorical feature becomes an array whose size is the number of possible choices for that features. So we create a data frame of country, different countries here. Wonderful. They use get dummies. Pandas provides a very useful get dummies. So once we'd seen that, gives a great example there. Beautiful. We could go to the get dummies page, but we already have that open. Get dummies. Convert categorical variable into dummy/indicator variables, which is I'm not sure why they use dummy indicator variables. I just treat this as another name for one-hot encoding. Come down. We see some examples with pandas. There we go. All right. So let's just run some code and see what happens. Rather than diving into documentation, who needs the docs when you can just run hundreds of different little mini experiments and figure things out for yourself? No, that's not to say that documentation is actually very valuable. So get used to reading documentation, but also get used to writing lots of code. So let's see what happens if we run this. Data frame object has no... we can't run it like that. I'm eating my own words here. We have to run it like this. pd.getDummies, then pass it our data frame. Come on, Daniel. pd.getDummies. Let's try one-hot encode our data frame. So it's all numbers. And what do we call our data frame? Insurance. Oh, yes, look at that. Okay, that's what we want. So we have age, BMI, children, charges, and now for the columns that were categorical columns, such as sex, we have sex, female. So see here, this first sample has a value of female, so it gets a 1 for the sex underscore female column. And then for the sex underscore male column, gets a 0. And then were they a smoker? Yes, they were a smoker. Oh, maybe why? That's why their charges are so high. So they get a 1 for the smoker yes column. And where were they from? They were from the Southwest. So they should have a 1 in the Southwest region. Wonderful. Okay, that looks good. Now, we might actually save this to a variable, insurance underscore 1 hot, and then insurance 1 hot, and dot head. Excellent. All right, so now we have a few more feature columns. So because charges is still the column we want to predict. So we want to use all of these columns, age, BMI, children, sex female, sex male, sex no, smoker no, smoker yes, region northeast, etc. We want to combine all of those and learn the relationship between what charges equals. So we'll probably end this video here before it gets too long. But if you want to have a here's a bit of a challenge too. If you want to go ahead, maybe we'll, in the next video, create X and Y values. So features and labels. Have a go at creating the X and Y values. Then we'll need to create a training and test set. And then we can build a neural network. So here's your challenge. If you want to go ahead, create training and test sets, and then build a neural network. It'll be sort of like Model 2 above, but it might have different input and output shapes, or we'll see. But that's your challenge if you want to go ahead. Otherwise, in the next video, we'll start to tackle these 3 things. How'd you go? Did you take on the challenge? Did you create X and Y values, features and labels? Did you make a training and test set? And did you perhaps even build a neural network, sort of like Model 2 above, to find the relationship between our features and target variable? If not, that's perfectly fine. If you did, wow, that's incredible work. Otherwise, either way, we're going to go through each of these 3 steps in this video. So let's split these off. I think the command is command M minus. Yeah, there we go. If you want to split a cell, so command or control M minus in Google Colab. So we have 3 different things here. This is what we have to do. All right, create X and Y values, features and labels. Let's do this. X equals. Now, what did we say before are our features? Basically, every column except charges. So let's, how can we do that? We can drop a column. So insurance, 1 hot, dot drop. And we're going to drop charges on the first axis. I believe that's how we do it. If not, we can find out in a second. And then Y is going to be just this column. So let's make sure we can get that. Insurance, 1 hot, just charges. Wonderful. Okay, now let's view X. X dot head. First 5 rows. Wonderful. Age, BMI, children, etc., etc. Got a fair few columns there, and let's view Y to make sure. Remember, always visualize, visualize, visualize. Beautiful. There's the charges there, which are all float 64s. Now, these are in a format of, right now, they're in a format of a pandas data frame. However, we're going to see very shortly that we can turn them into formats capable to be used with our neural networks. That's actually probably going to happen automatically because we're about to create training and test sets. Now, previously, we'd indexed our data sets going something like the first 40 examples are training examples. However, there's a much better function to create a training and test set if you've got a feature matrix and a label vector. So we're going to use scikit-learn train test split. This is a very popular function. Model selection, train test split. Remember, creating a training and test set, probably one of the most important things in machine learning. That's why this function is so beautiful. So split arrays or matrices into random train and test subsets. Wonderful, that's exactly what we want. Oh no, we don't need to copy that. We can just import sklearn.model selection train test split. Let's see how we can use this. From sklearn.model selection import train test split. So if there's one function from scikit-learn you want to remember, it's this one. Very, very popular. So we go here, xtrain, because it's so useful. xtest, ytrain, ytest equals train test split. And then we want to, can we get the doc string? Or is it not imported yet? Not imported yet, that's all right. I know you need an input, but we're not up to that yet. Here we go. What's the doc string? Split arrays of matrices into random train and test subsets. Okay. So we want, what does it take? Arrays, sequence of indexable with same length or shape 0. Allowed inputs are list, numpy arrays, scipy sparse, matrices, or pandas data frames. That's us. That's what we have. Beautiful. Test size. If float should be between 0.1 and 1.0 and represent the proportion of the dataset to include in the test split. So before we made an example, right up the top, right back up here, in the 3 sets, we used an 80-20 split, meaning 80% training data, 20% testing data. That's a very common split, very useful split for our problem. So let's keep it at that. And I just want to see, what's the example here? This is where I got this line of code, by the way. Okay, train test split, it passes x, y, test size equals, they've used a 33% test split, and they've set random state 42 to make sure that the data is split in the same way each time. So otherwise, if you don't set the random state, the split will be random. So let's go in here. I'm going to pass x, y. Oh, I've got caps lock on. Goodness gracious me. Test size equals 0.2. And I'm going to set the random state. They've set 42, so we'll set 42 too. All right. And let's see what happens here. We'll go len x, just to see the length of x overall. And then length of xtrain and length of xtest. What's going to happen here? Beautiful. Look at that. It's created our train and test split. So this is how many were originally in X. And because we've set the test size to 0.2, our test data set has 20% of the sample. So if we were to go 0.2 times 1338, what does it give us? Okay, it's going to be around, it's been rounded up. All right, nice and fair. And it's also random. So if we go xtrain, what does that look like? Ah, all right, all these indexes are randomly shuffled. Beautiful. That's what we're after. So let's get out of that. Now, how might we build a neural network to take in xtrain and ytrain and learn the relationships between the two? So the hint is, it's sort of like Model 2 above. So if we go, we get another code cell here, model2.summary. What does Model 2 look like? All right, so we've got 2 layers. Very familiar with this Model 2. How about we just recreate it? What should we do? TF, set the random seed first. Random set seed, 42. Nice. Now step 1 is create a model. How do we do that? We go model, or actually we'll call it insurance model. There we go. TF. Pretend we're working for a large insurance company and we've been asked to model this data set so that when Sally Smith comes to buy insurance off us, we know if she tells us how old she is, where she's from, if she's a smoker or not, we know how much we should charge her based on our other customers. That's what we're doing now. There we go. Now, what do we do always after we create a model? Step 2 is we compile it. Compile the model. And here it's called insurance model.compile. What's our loss function going to be? tf_losses. What have we been using? MAE. mean absolute error. We can keep it like that. We could even change it to MSE if we were feeling a little adventurous. But since we're going to stay with a similar experience to what we've been running, we'll keep it as MAE, optimizer equals TF Keras optimizer dot the old faithful stochastic gradient descent, SGD. And the metrics we're going to put here is mean absolute error. Beautiful. And now, number 3 is we fit the model. Now, I said before we were going to format our data into a way that it's going to work with TensorFlow. So right now we're writing TensorFlow code here, but up here, this is Pandas code. Pandas, scikit-learn, and now TensorFlow. I wonder if this will work. Do you reckon it'll work? If in doubt, run the code. You ready? We're about to build a neural network model on 1,000, or really because we're fitting on the training data, it's just over 1,000 rows of data, which is a big increase on what we've been working with so far. So don't hold your breath. 3, 2, 1. Is it going to work? What did we miss up? I knew there'd be an error. Spelt insurance wrong. Oh, what an anticlimax. All right, 3, 2, 1. And again. Here we go. Here we go. Now all the typos come out. All right, third time lucky. 3, 2, 1. I'm done. Oh, you typed in. All right, no countdowns anymore. Just fit the model. Boom, look at that. All right, now this one takes a slightly little bit longer because we're working with more rows. So we come down here. Does our MAE decrease as we're going up? It starts off around 8,600 and it finishes around 7,100. Okay, so a fairly good decrease. And we're just going to get rid of this cell here. Wonderful. So what do we do now? We just train a model. Oh, and yeah, by the way, we didn't even have to reformat this into tensors. The reason being is because Pandas is built on top of NumPy. So really, when we see it like a Pandas data frame, this is actually a big NumPy array. And when we pass that to TensorFlow, it automatically knows how to deal with NumPy arrays because we've seen tensors work with NumPy arrays before. So what's next? After we've trained a model, what should we do? Should we evaluate it on the test data? Great idea. Let's do that. So check the results of the insurance model on the test data. So insurance, how can we do that? We can use the evaluate method, evaluate on X test, Y test. Let's see how it performs. All right, okay. So on the test data set, it's performing even just a slightly little bit better than on the training data set. That's pretty cool. So now what might we want to do? What is this error telling us actually? Mean absolute error. It means that on average, our model is wrong by about 7,000. Now, is that number large? Is that significant compared to the other values in our data set? Let's have a look at our training variables. Y train. Whoa. So if our model is off by 7,000, what's the median, the middle number of our target variables? Wow. So the median variable, or actually what's the mean as well? 13,300, 9,500. So right now our model's pretty substantially wrong because, I mean, look at this. The average value of Y train, so the average insurance cost, is 13,300. So, and our model is on average off by 7,000. That's pretty significant considering the total amount is only 13,300, well, that's the mean. But the median, it's even worse. It's only 9,500. So if we're off by 7,000 there, we might be charging someone 2,000 when they should be being charged 9,500. So naturally, what might we want to do? If you guessed improve our model, you'd be 100% correct. So let's, in the next video, right now, it looks like our model isn't performing too well. Let's try and improve it. So we're going to start to run some experiments to improve our model. But before I do, again, I'm going to issue you another challenge. If you want to go right ahead, we've already run some experiments to improve our models. How about you try running some very similar experiments on the model we just built here? Maybe you add an extra layer, maybe you change the optimizer, maybe you train for longer. Give it a play around and see how you go. But otherwise, we'll try a few experiments in the next couple of videos. How'd your modeling improvement go? Did you get a better MAE score? Was it lower? I hope yours did better than the one we first built, but if not, that's all right. We're going to see if we can improve it now. So what should we do first? When we did it up here, we did some experiments. So the first thing we did was, okay, we added an extra layer. Okay, let's try that. We'll come down here. A larger example. First experiment. Might write this down actually. So to improve our model, or actually we'll put try. To try improve our model, we'll run, let's do 2 experiments. So one can be add an extra layer with more hidden units. And then 2 can be train for longer. And then I'll leave the rest up to your imagination. Insert your own experiment here. You can put to use what we've learned. So how about we recreate the model? We'll try the first one. So add an extra layer with more hidden units. So set random seed and then TF random set seed. Wonderful. Now, number 1, create the model. So TF Keras, we need to go insurance. Insurance, what do we call it before? Just insurance model, right? Insurance model 2 equals TF Keras sequential. Wonderful. And then we should go TF Keras layers. Maybe the first one here has 100 now. Then TF Keras layers dense 10. And then TF Keras layers dense 1. Is that an increase? What was our first? Yeah, we only had 1 layer with 10 there. So this model has an extra layer with an extra 100 hidden units. So if we come down here, if we go there, 2 is compile the model. And we want to go insurance model 2 dot compile. We're going to go loss equals TF Keras losses dot MAE. What's the optimizer? TF Keras optimizers. One day I'll get this right. SGD, beautiful. And then the metrics can be MAE as well. And now let's go number 3 is fit the model. Is insurance model 2 dot fit X train Y train epochs equals 100. All right, you ready? This time we're going to set verbose equal to 2, so we don't have a massive output. Verbose, sorry, equal to 0. What did we get wrong here again? Oh, metrics equals MAE. All right, we finished there. Again, we get some warnings. I was just saying that our data types are maybe not optimized, but the beautiful thing is that TensorFlow fixes those for us. And now we can go evaluate the larger model. So insurance model 2 dot evaluate. Hopefully, because we've added more hidden units and an extra layer, we've given our model more potential to learn. So, well, that's at least in theory. Did it work? Oh, what do we get wrong here? Maybe we should output the training. Nan. Dense 100, insurance model 2. Insurance model. All right, now we definitely have some troubleshooting to do. What have we got? X train, Y train should be the same. Maybe our model is too complex to learn anything. So we might have built a too big a model. What's another lever that we can tune here? We could remove this layer. Let's see if we just remove that layer. Does this work? Okay, so it works there. This is some good troubleshooting. Now what if we keep that layer on and try again? We get loss is NaN. If you ever see your loss or MAE as NaN, it means that there's probably something wrong with your model.